Welcome back. In this submodule, we'll discuss the domain and range of our original 6 trig functions: sine, cosine, tangent, secant, cosecant, cotangent. So the question is, what types of inputs make sense for these functions? Are there any that generate pathological outputs? And then what kinds of outputs can be achieved? Those are the questions of domain and range, and we'll investigate them here. So let's start with sine. So here's a plot of sine of x. So you can see on the x-axis I'm going from 0 to 10 and also from minus 10 to 0. And I clearly see this periodic structure. So there is one period over this interval, for example. So a period is just a length in which I repeat myself. Okay, so taking a look at this plot, which I generated in the scientific programming language MATLAB, but you can, of course, do with your graphing calculator, we see many different things. For one, there don't appear to be any issues with the domain. It seems like every input is giving me an output. So this is good. This tells me that the sine function is defined for all inputs x. So the domain is minus infinity to infinity. On the other hand, it looks like the biggest value I'm getting is 1. Right? I reach some maxima here. And the smallest value I achieve is minus 1. I hit some minima here. So this tells me my range is not everything. My range is only minus 1 to 1. And I include the endpoints because I achieve them. So remember, these square brackets mean include endpoints. So let's do a quick exercise. I'm going to ask you to compute the domain and range of a transformed version of sine. So what we'll do is we'll try to sketch the function and then interpret the domain and range. So I'm just setting up my axes, which is a good habit for you to get into. Let's make a table. So what happens when I plug in 0 here? Well, sine of 2 times 0 is 0. So 2 times that is 0. So I just get the plus 1 there. At pi over 2, that's 2 times sine of pi, so 0. So I get 1 again, and then here I get 1 again. So the picture is like what? Well, maybe we need a few more points here. Let's do pi over 4. So at pi over 4, I have 2 times sine of pi over 2 plus 1, which is equal to 3. So it looks like the picture is going to be something like this. So what can we say about the domain and range? Oh, and of course we're going to be periodic. Okay, so the domain, well, there's no issues here, so I should be able to use all of the numbers. And then for the range, it looks like my largest value is 3, and my smallest value is at minus 1. So the range is minus 1 to 3, where I include both of them. So this is a nice example where if you had a graphing calculator, you could easily see the domain and range. But for the CLEP exam, there'll be a whole section in which you won't have access to the calculator and will be asked about trig functions. So you should be comfortable doing some basic plotting exercises like this one. So let's look at cosine now. So the picture is very similar to the picture for sine. The key difference I want to draw your attention to is that at x equals 0, my output is 1. Whereas for sine, at the input x equals 0, my output was 0. But otherwise, we have very similar structure. It is 2 pi periodic. So this is 1 period. And from a domain and range standpoint, they're basically the same. I have no problems with any inputs, so the domain is infinity to infinity. And there's still minus 1 to 1, because my minimum value is achieved at these minus 1 values, and the maximums are achieved at 1. So very similar to sine. Okay, so we'll, as an exercise, use our knowledge of the domain and range of cosine to compute the domain and range of secant. So how are these related? Well, now we have to go back and remember our trig identities. So remember how I said all of these things build on each other. If you forget how secant relates to cosine, don't worry about it. Go back, watch the slides again later, and you will remember the connection. These things don't come the first time. So, but the key point here is that if I'm looking at secant of x, that is 1 over cosine of x. So I can use this information to determine the domain and range. So the domain of secant is everything except when cosine of x is equal to 0, because then I would be dividing by 0. So when is cosine equal to 0? Well, that's at pi over 2, but also at pi over 2 plus k times pi for any integer k. So unlike sine and cosine, which had domain as everything, secant has limited domain. I have to remove the places where cosine is 0. How about for the range? Well, I know that the range of cosine is minus 1 to 1. So what is the domain of secant? Well, it's everything I get by doing 1 over something in the interval minus 1 to 1. So I can think of this as, I'll put this in quotes since, this doesn't totally make sense. 1 over the interval minus 1 to 1. So what is this? This is minus infinity to minus 1 inclusive, and then also 1 to positive infinity. So the range looks very different here. The things that secant can achieve are small values. I can't get too close to 0, but it can get very, very big. Whereas cosine was the opposite. Cosine can get close to 0. In fact, it gets to 0. But it can never get bigger than 1 or negative 1. So the secant is 1 over cosine means roles are reversed. Secant has big values, cosine has small values. So we can use this information actually to plot secant. So where are my problem issues? Well, my problems are at pi over 2, like 3 pi over 2. So secant's going to look something like this. And like this, and then it's going to come down again. So here's just a rough sketch of secant. Notice that it never gets any smaller, never gets closer to 0 than 1 and minus 1. It also has these sort of strange behaviors around pi over 2 and 3 pi over 2. These are called asymptotes. We'll discuss them in module 4 in more detail, but they are useful for plotting. So I'll say that these are called asymptotes. Like to learn more about how these asymptotes play a role in trig functions, please take a look at our reading. It'll go into details for this for other trig functions in addition to secant. Tangent, we've already seen, has asymptotes. So does cotangent and cosecant. So now look at tangent. Here's what we've essentially already seen. I've just stretched it out a little bit. Notice that the domain here is only going from pi over 2 at this endpoint and negative pi over 2 here. And we see that, is the value 0 at 0, and then it's rapidly blowing up as I approach pi over 2. Okay, so this is a very important sketch to have in your mind's eye, that unlike sine and cosine, always stay bounded and just keep oscillating back and forth. Tangent has blow up. It has asymptote. So this affects the domain and range. We see that the domain is everything except at multiples of pi over 2. Actually, this is not quite. It should be pi over 2 plus pi times k for some integer. So we see that we're at 0 here, and then I go over to pi, we're at 0, go over to 2 pi 0 again. So we see that there's there's one period here. But it's smaller than it was for sine and cosine. It's only length pi, not 2 pi. And we see we have problems at pi over 2, pi over 2 plus pi, aka 3 pi over 2, minus pi over 2, minus 3 pi over 2. So my issues are at these points. So the domain is restricted, but the range is everything. Clearly I'm going to get all negative numbers from, say, this part here, and I'm going to get all positive numbers from this part. So tangent really behaves very differently than sine and cosine. It has restricted domain. I can't be evaluating tangent at pi over 2 plus pi k for any integer k, but it's everything range. So that's sort of a nice consolation. Okay, so let's use this as an exercise to study the domain and range of a transform function of 2x over pi. So all we really need to do is figure out where are the issues with the domain here. Where are the asymptotes? So think about it like this. The problems are when x over pi equals pi over 2 plus pi k. These are the places when tangent's not defined, when I have these asymptotes. So now I just need to figure out what values of x will lead to this problem. So it's just a simple algebra computation. I'll divide by 2 and multiply by pi. So x over pi should be equal to pi over 4 plus pi over 2 times k. So x is equal to pi squared over 4 plus pi squared over 2k. So these are the things I have to avoid here. So my sketch is something like, well, what's pi squared? That's about 10. So these are where my asymptotes live. So our sketch is something like this. Now main is everything except x equals pi squared over 4 plus pi squared over 2 times k, and the range is still everything. So when you're given trig functions where you've modified the argument somehow, where you've replaced x with x times something, to find out how this acts the domain, just solve this type of algebraic equation. I wanted to find out when 2x over pi was going to be equal to one of my bad points. So I just solved for x, which was a little tricky. I had to multiply by and divide by 2. So the values of problems are funky looking. I mean, pi squared over 4. I mean, that's it's hard to figure out what that really, what number that's close to. Should be able to do this with a CLEP exam. So if you have issues with this the first time, I strongly encourage you to read our supplemental texts and practice lots of examples. This is certainly in your grasp, but like all things that are difficult, it just requires some practice.